And also how one can apply it to the problem of pseudo-holomorphic curve in simplex geometry. But maybe at the beginning,
Applies to what?
Application to simplex topologies and pseudo-holomorphic curve. Maybe I need to start with some introductions. So I mean, background is the following things. I mean, nonlinear PDE in differential geometry is a kind of old topics, but at some point in 1970s or 60s, it gets very much exciting areas. But then after a while, there are some new way to use nonlinear PDE. I think that came from Donaldson's work on four-dimensional topology. So his very important idea is somehow not only solving single nonlinear PDE, he considered a kind of a family of solutions, so the set of the modular space of the solutions. And the very important idea is that modular space of solutions has often a fundamental class, and this fundamental class plays a very important role in his theory and its application of Yang-Mills equations to four-dimensional topology. So typically, he first constructs some kind of a 5 manifold which bounds given 4 manifold. So fundamental class of this 5 manifold is a kind of a bounds original 4 manifold. So that plays important role. And then the next application is he used this fundamental class of modular space of solutions, and its homology class is very interesting and important invariant of four-dimensional topology. And then that happened, I think, at the beginning of 1980. And then Gromov came up with an idea that not only Yang-Mills equations, but also nonlinear Cauchy-Riemann equations can be used in a very similar, or I mean, also, and to study simplistic manifold. And then he cooked up kind of really new result, which kind of make simplex topology to start. So before that, there is no simplex topology so much. And then after this idea that you can use fundamental class of modular space of nonlinear Cauchy equations, it gets very exciting areas. And there are several people, and like I think there's some MacDuff and there's Freyers, and those people came up, and then these areas kind of start to be interesting, and it, I believe, to keep to be interesting for 20 or 30 years after that. And you know, as I mentioned already, Freire, and one big idea of Freire is that one can not only construct invariant that is a number, but also some more sophisticated things like groups. And so them kind of things are keep going. And the invariant this Gromov cooked up is so-called Gromov-Witten invariant. And Gromov-Witten invariant is kind of written kind of.
I have a question. Why is Witten involved in this?
I think Witten wrote down some path integrals, which should calculate this Gromov-Witten invariant independently. So that's the physics people's understanding is just some supersymmetric path integrals. And the supersymmetric path integral gives a number. And if you understand this number, this path integral correctly, then it should be this Gromov-Witten invariant. So that's the reason, I think.
And what was the relative timing of Witten's paper and Gromov?
I think Witten's paper is slightly later. But you know, I think one big thing is which came from this Witten's formulation is I think this associativity of quantum cup product follows from this Witten's formalism, and Gromov did not know it before this kind of things are coming. So some of the key feature of this Gromov-Witten invariant certainly came after the discovery of this
algebraic structure.
Yeah. And so then
those come from gluing theorems, which in the path integral are sort of, that's almost obvious from the path integral, but in
I mean, he, of course, He try to realize this kind of associativities. Of course, this physics proof does not work, is not good enough. So we need to kind of rephrase this what physicists do to understand. But I think it's a Buffer who mentioned this associativity very clearly. It's a kind of quantum rings. It's a kind of I looked at it in there are series of kind of collections of papers edited by Yao and those people, mirror symmetry. And the first of volumes, Buffer wrote something about the ring structures on this invariant. That's the first place I looked at, and that's the kind of beginning of 80s. And a few years later, several people start, mathematicians understand it and it's proven. Okay, so then, as usual, Gromov do it in kind of most primitive and kind of beginning case, and he has gone. And so in his case, somehow he just proved in some interesting but special case like a CP2 or even CN. But then people try to cook up this kind of invariant in rigorous ways. And then at the beginning somehow, the problem is the modular space has a fundamental class. So you have a modular space, some M, and the key idea is you have to take this fundamental class in some homology group. But then it often happens that the modular space itself is not a smooth manifold. So if you just take randomly, just take some PDEs, then the solution space is not a smooth manifold. So in general, not smooth. It's very singular. So the singular space, and this is even worse. One important feature of this Gromov theory is just you need to consider not only integrable complex structure but also almost complex structures. In that case, the situation is even worse. In a case when this is a kind of usual world of complex manifold, then this is at least some kind of analytic space, complex analytic space. So you have some control. But if you go to this real world, kind of almost complex world, then I think in general this can be everything, like a Cantor set. So to think about a fundamental class of a Cantor set is a quite ridiculous thing.
That's HM of what? Inside the trunk.
Okay. This is correct. You take check homology, then it is correct. But if you just usual homology, as I said that you take usual homology. This modular space is still, as I said, horrible. So homology group of that horrible thing it does not make sense. So.
And do you require that thing to be compact for the homology to be defined?
Yeah.
Okay, so and that you are writing there is a compact object.
Yeah, compactifications, yes. But this is just a kind of very vague introductions. So the comes idea, so at the beginning, so people use some kind of a geometric perturbations. And in a Yang-Mills theory, there is a famous theorem by Uhlenbeck, which says that you take metric G on 4 manifold, then you take this metric generic, then the modular space of the solution of Yang-Mills or anti-self-dual Yang-Mills equation is smooth manifold. So people can use these theorems. But actually, this is not necessary to use this kind of theorems, but you can take another perturbations. For example, I think if it's not SU2, probably this theorem is not known. So if you consider just more general Lie groups, then this theorem is not known. But this is the particular way. And in this,
It will have to be false, Kenji, because SU2 sits inside your group. Any SU2 solution, which you might have to have because of Donaldson, will be singular members of this.
Yeah. But not only singular, but kind of more horrible, right? They do not have any fundamental class. So if it's singular, but still it can host some fundamental class, but it's even fast. Then in this situation of this nonlinear Cauchy Riemanns, then the idea that which starts at the beginning is that you have J. J is a almost complex structure. Then if you take this J generic, then we can make this modular space of holomorphic map to be smooth manifold under certain assumptions. And this, then somehow under this certain assumptions, the theory develops and people cook up many interesting and important theorems. So that's happened in this 90s and the 80s and 90s. So under certain assumptions such as monotone, exact, I don't want to explain what it is because I don't want to use this kind of assumptions, or at least some semi-positive.
I don't think anybody can prove the compact space is smooth.
Really?
Even under these assumptions.
Even monotone?
Well, the main term is certainly smooth. But then you do the gluing.
Yes. Yeah. So one can say it's not smooth, but has a partial fundamental, but has a fundamental class. In a case, yeah.
Topological manner.
Yeah. In a sense, if the singularity is enough small dimensions, like codimension 2, then it has a fundamental class that usually need. And if you honestly say everything is smooth, of course it's harder. So, but somehow, I mean, so under certain geometric assumptions, one can prove that at least this moduli space has a fundamental class, and you can use this fundamental class. But then somehow, this kind of assumptions are always assumed, and there is a general feeling that this kind of assumption is kind of unnecessary. By certain reason, we need to do it, but we don't need it. And the idea is something came from the late 90s that we can do it by using some more abstract ways. So here, as you see, that we have this geometric perturbations, like Riemann matrix, or almost complex structures. So you know that after you change your things, which equation you are solving. But then somehow, in each case, you need to find some parameter, geometric parameter you move, so that your spaces are smooth. But then it's a kind of, first of all, the argument can be a bit ad hoc, because in each stage, you need to find some particular way to perturb your equations. And also, one advantage, it's still geometric. But somehow, and we don't know that that kind of approach can work always. So at some point in the 90s, there is a kind of ideas about this abstract perturbation, somehow virtual chain, virtual fundamental class. And then people use this virtual fundamental class in this so that basically all the moduli space of holomorphic curve is has a fundamental class in expected way under any assumptions, without any assumptions. That actually is correct, and that's something I want to explain in this series of talks. So how to make all the moduli space kind of correct, have a fundamental chain or cycles in correct dimensions. Okay. Now, so this is a very brief, yeah.
Is this in the holomorphic curve space or in general?
Pardon?
I mean, how general is this technique?
My understanding is if it's non-compact, you need some convexity. But if your compactness is okay, any symplectic manifold.
It's in the symplectic case.
Or in this particular case. Actually, I have some ideas how to go to gauge theory, but it's still beginning. So.
No, from a topology point of view, I mean, it's really a cohomology class that's there. And making it transversal and all that is just finding the Poincare dual.
Yeah.
But isn't there some natural setting where you have a cohomology class, even using infinite dimensions? I mean, like maybe using...
I mean, there's an issue of compactification.
One big issue is the compactness. So I need to assume something is compact. So we need to at least first cook up some modular space itself, which is compact in a reasonable sense. And then you can take small neighborhood.
Yeah, a small neighborhood, but in an infinite dimensional space.
Yeah.
Right, but I mean, just that neighborhood has the information. I mean, the point is the neighborhood has the information.
I don't think, the problem is the modular space itself and its neighborhood. My impression is rather chaotic. And somehow, if you just change this J, for example, then they change in a kind of unpredictable ways. So something which remains to be kind of invariant is a kind of homological information you cook up.
Yeah.
So if you just look at that space itself, probably it's hard. I mean, this case,
if the set of solutions is compact, then the neighborhood of the set of solutions has the information.
Yes, that's right.
Space are you talking about? The
Any
space,
space.
well, I mean, the
No,
space
but I mean, that's
maps
the,
or something.
the principle in topology. It's just the homological information of something like that is contained in the neighborhood.
Yeah, I think that's basically what these virtual techniques are doing. Mm-hmm. But the problem is there is a kind of difficulty to define this kind of neighborhood in a way, kind of canonical way. I mean, so if you try to cook up some virtual neighborhood, then usually it is a kind of depends on various choices. And there's a big effort to construct such a things in a canonical way, in a way independent on this artificial choice. As far as I'm understanding, in the finite dimensional approach, the most closest to this, realize this is what Dominic Joyce is doing. So he does take some kind of very...
He cuts off the infinite dimension.
Yeah.
And then it's some finite dimension.
Yeah. I mean, that's something. Yeah. That's something I want to explain. But this cutting off always involves choices. So to get something canonical, then one need to kind of weigh how kind of to define some notions of spaces, so that this finite dimensional things are in a sense canonical. That's something I cannot do yet. So what I want to do is I will define the notion of Kuranishi spaces, space with Kuranishi structures, and what I cannot do is to define morphism. So I try to do it for a while, but I never it's not yet successful. So you have a notion of Kuranishi spaces. It has fundamental class. Notion of Kuranishi structure or Kuranishi spaces. Yeah, that's something I want to explain. This technique, we can define it, but it's some notion of the spaces, and you can associate it to many of the modular spaces, and you can use it to cook up fundamental class, and you can define the well-defined class of the fundamental class using some cobordism argument. But you try to prove that this kind of spaces is well-defined, independent of the choices. First of all, I think it's better to cook up some category of the space with Kuranishi structure, Kuranishi space, category of Kuranishi space, and that I don't know how to do it. Probably the correct thing is probably we cannot do it in one category. So what Dominic Joyce told me that at least we need two categories. so that's another problem. So I don't know how to do it in one category.
Conceptual problem.
Yeah, it's
I mean,
that's a conceptual problem.
properly formulated.
Yeah. I mean, in algebraic geometry world, people can construct many singular algebraic varieties, and the scheme itself is just a kind of notions. And what's nice is that the scheme is a very good category. Everything is a kind of fiber product is very defined, and the morphism is very defined. So the dream is we can cook up this similar category in a world of differential geometry. It is much harder because in scheme somehow that topological space itself is just not so bad. It's an analytic space. But in our world, it can be a contour set, with certain structures. So what I mean by the structures? And that's difficult problems. But what I do is somehow to take some small neighborhood, it's a smooth manifold, and then this choice is a bit ad hoc. However, this choice is a kind of well-defined up to cobordism. So this is good enough for certain purposes, but you want to kind of really do beyond this homological constructions, then you really need a space. Then this non-well-definedness become an issue, and I don't know how to do it. On the other hand, I don't know any kind of concrete problems we really need this something beyond the homological chain complex.
Well, yeah, but don't give up for that reason.
Yeah.
But is it true that you will, in the end, produce a homology class in a neighborhood of the solutions, the moduli space,
Yes.
in the space of all
Yeah, I mean, that's
Space of all
J's?
the space of not all J, but the space of all maps. So honestly speaking, you consider the space of all maps from sigma to X. This is the Lima surface, and this is the arbitrary dimensions. But then you want to consider the space of all maps. It's infinite dimensional spaces, but not you cannot construct homology class here because you need the compactifications. So you have to.
Let's not worry about compactification right now. So you're going to fix a J
Yes.
and just look at the maps.
Yes.
That's compact.
Then you're going to produce, in the space of maps, you're going to produce a homology class.
Yes.
Concentrated in an arbitrarily small neighborhood
Yes.
of the moduli spaces.
Yes. Yes, that's right.
That's a correct thing.
That's correct thing. Even after compactification, it's correct.
Yeah.
But this small neighborhood, the topology of this small neighborhood is not canonical. If you include all the maps, you have some topological information. Your homology class lies there. But you consider the neighborhood of the modular space. The homology group of the neighborhood of the modular space, it's unpredictable. There's no, you cannot calculate it.
And just to confirm, is it going to be a singular homology class or what kind?
It depends. There are various theories. So, for example, after cooking up this general finite dimensional reductions, you can do many kinds of theories. At least we did singular homology and drum homology. There are other possibilities like Morse homologies, and Dominic Joyce introduced some other. It's kind of.
What does drum homology on this singular object mean?
We take this small neighborhood. We have drum differential forms. We use it.
So this small neighborhood is a smooth thing?
Yes, it's a kind of union of some smooth manifold. You can define differential forms on it. And the singular homology also has if you just state to this modular space itself is not behave so good. There is another idea using check homology. And check homology behave better. because this singular thing is a kind of a projective limit of smooth things. So I think those are you should use it, and yeah.
I mean, I have a slightly different point of view, which I'm actually going to give an overview on Tuesday.
Yeah.
And I will say, I mean, there are different ways of doing this. So I'm not going to say.
Yeah. But the check is yeah. I mean, you just try to stick on defining some homology class in the modular space itself. I completely agree. The best choice is check, because the modular space is a projective limit of smooth things. So check homology might be better. Even in the Cantor set, I think check homology of Cantor set might be better than singular homology. And yeah.
So I want to come back to what Dennis and John were saying. There is a well-defined topology on the configuration space of all maps. So the neighborhood of this modular space of J-homomorphic maps does have a well-defined topology. The thing that you're doing is you're just going to construct finite dimensional approximations to a modular space.
Yes.
But eventually they sit in this infinite dimensional neighborhood. And as Dennis was saying, the whole information is encoded by this neighborhood.
Yeah.
It's encoded by the configuration space, and there is an infinite dimensional bundle.
Mm-hmm. Yes, that's right.
So this is what Dennis was asking at the beginning.
Mm-hmm.
It's just a question of how you extract information out of it. But the topology is there a priori.
Yeah.
And Lin can define topology on a configuration space.
Yeah, but the one problem is about compactification. That's serious thing.
No. So the modular space is compact, but it's in this infinite dimension.
I mean, the ambient space is not. Yeah.
Ambient space is not compact, but.
I mean, ambient space, you compactify, it doesn't lie on this space of maps because it came from singular things.
No, it does lie inside of the space of maps because you can define configuration space on the space of single maps also.
Yeah, but you have to glue them.
But you still can define a topology on this thing.
Yeah. Yeah, in that sense it makes sense, yes.
So the topology is well defined.
Yeah, that's okay. That's true. I mean, in this polyphore type things, and also this Ganliu-Tian's approach, they use more on this infinity measure things. But then using they need compactification. It's just a subset of the mapping space, but you need kind of something which singular became singular. And then if you try to do analysis on these compactifications, I mean, on this extra thing, it gets harder. But at least topology should work easier. In that sense, you are right.
My first remark was just in finite dimensional topology, if you have some compact set and you think there's a homology class there, then it's sort of in the neighborhood as a dual cohomology class. So that's sort of kind of a tautology. You have Poincare duality and stuff like that, right? So that's kind of what I was talking about first, that you don't really have to, if you have two cycles that intersect badly, you look at the intersection, it's compact, and in the neighborhood of that, the intersection theory is there, but in finite dimensions. That's what I was thinking. And then this is like an infinite dimension.
Yes.
But then I think it's not enough just take that naive thing and transport it in infinite dimensions. You also need the section that is intersecting with the zero section. So the infinite dimensional neighborhood and the section, or whatever, or the equation, but then it has the information. So I think
that's right.
That reminds me of Max's semi-infinite theory, where there has to be an action functional controlling the infinite dimensions. And stuff like that. I mean, I think I haven't heard the right conceptual wish. I mean,
but this is finite dimensional cycles, not infinite dimensional cycles. So it's different from Freire theory. Yeah.
Dimensional.
Yeah.
But then you need this. But you also have the equation.
Yes. That's basically the idea of these Kuranishi structures.
Right.
The analogy with finite dimension is flawed because in finite dimension, the proper analogy is a non-compact space. So you don't have these duals unless you're really lucky or you're really careful. That's the problem. So you want to compactify even in finite dimension. You might need to add ends.
Yeah, but the fact that Witten and the physicists can find it by just writing down in infinite dimensions this meaningless expression and find the right answer. I mean, that suggests that we don't have the right formulation, right? I mean, they could just find the answer with their formalism. But the action functional is there in their formalism. That's controlling the infinity. So we don't have the right formulation. We're proceeding as mathematicians who think something is understood when it's proven. It's not true at all. In my opinion, that's my view
Well, I think you should talk to Helmut Hofer because you see.
No, I talk to him all the time. We end up shouting at each other. We don't agree. I mean,
agree.
there's understanding and there's proving with details. These are both valid perspectives.
But I think that if you want to look at the ambient space, then polyfolds is a very good way of coping with the analysis because one thing we haven't mentioned at all is the reparameterization group, which is with sort of standard analytic tools does not work differentially. And in the polyfold setup it does, and therefore you have to begin with a much better setup. I mean, you have your bundle, you can quote it out by the reparameterization groups, you've got your section. I mean, you have a much better chance of making a nice sort of conceptual view of what's going on. But the trouble is that means redoing all the analysis. And, I think that Kenji and I were sort of starting with more standard analysis, and then what we're doing is not getting the beautiful conceptual picture you want. But we're trying to get something correct. I mean, the first thing is to have something correct, I think. And then, you know.
I think understanding is the first thing.
Well, but you see,
You can't write papers, though.
Do I understand you correctly that you're not confident about, I could look at a small neighborhood, I could look at a sequence of neighborhoods around the moduli space,
Yes.
and I could ask about their in-dimensional homology. Let's
Yes.
more compact.
Yeah.
And maybe you're saying that isn't a rank 1 group. So it's supposed to
Yeah.
and that you're picking out by some geometric construction a cycle and therefore a homology
yes.
class, and you're able to prove that if you did a different construction, you would get a homologous
Yes,
answer.
that's right.
But you're not proving the homology of this neighborhood is only got that one Z.
That's right.
Is that?
That's right. Homology of the neighborhood itself, I don't think makes sense so much because it so much depends on many things.
Well, I have this system of neighborhoods, I can take their homology.
I mean, it's a very small neighborhood of modular space.
Yeah.
The modular space itself, for example, you let us consider the case when the virtual dimension is 0.
Okay.
Then the modular space can be huge, like Cantor set. Then you take H0 of this neighborhood. Then it depends on which kind of things you start. You may have this Cantor set, you have just finitely many points, just 1 point. So,
Your equation or the family of equations.
yeah. So this finite dimensional reduction somehow already kill many things.
So this is related to what you were saying, Max. Yeah.
And also to counter what Ben said, for physics, the natural spaces in the space you get in, say, the Lagrangian version of the theory are the compactified ones, because here we're lucky in the closed case that we don't need to compactify. But in general, the natural space is a bigger one anyway. So whatever path integrals we're doing, I'm following down in this bigger space.
Okay, may I continue? So I just want to rather if you try start defining these Kuranishi structures, it's not so much simple things. So I just want to start explaining the most essential examples, but local things. And one thing I want to explain is that why we don't need to study group of diffeomorphism.
Well, you don't need to study what?
Group of diffeomorphism of Lima surface. That's I think one issue that people, yeah.
What? Go study what?
group of diffeomorphisms
Oh,
of Riemann surface.
Yes. That's something I want to explain.
Parameterization.
Yeah.
Study it. Oh.
Okay, so I just want to consider the problem. So maybe just the simple definitions. You have an X topological space, metrizable space, and we define notion of a simple Kuranishi neighborhood, Kuranishi chart of P.
What's the first one? X is what?
Metrizable, metrizable space. Yeah, my handwriting is not so bad as my pronunciation, but it's not so good either. Okay, yeah. So this notion is I want to simplify because for Kuranishi structures contain a bit more. So it's just 4 things. Already 4. It's not so much happy, but there are 4. Oh, really? So maybe I can never define Kuranishi structure while you are here.
New things.
So this V is a finite dimensional manifold, not necessarily compact. It's typically open. Finite dimensions. E is a vector space of some dimensions. And S is a smooth map. And C is a map from a zero set of S to X, and which is a homeomorphism onto a neighborhood of P. So the picture is very simple. You have some
Neighborhood of what?
of P. P is a point of X. So you have a X here, some horrible thing here. Yeah. This is the definition of Kuranishi chart. So you have a horrible space X, and you take some point P here, then you take its neighborhood. So this neighborhood is homeomorphic by C to S inverse of 0. And S is a map from B to R of N. And V is an open set of some Euclidean space. So that is a full picture.
So the neighborhood on the complicated X.
Yeah. So each point of X is horribly complicated, but you have a way to write these horrible things as a zero set of some smooth maps. So that is what this Kuranishi chart says.
Okay, so I mean, if the manifold and the map S were analytic, you'd be defining what's called a real analytic space.
Yes. But the point is that this S is just infinity.
Right.
I mean, this kind of things I think is going back to Kuranishi or kind of, I mean, old days. But kind of people think only in the case S is holomorphic, because in the case of holomorphics, S inverse 0 is not terribly bad. It's still something you can study. There are full study of holomorphics, a complex analytic set, which has a kind of a good structure itself. But if you go beyond the world of this complex world, then zero set of smooth map, you know everything.
Even do real analytic structure.
Yeah. But it's just smooth. And in the case of this J is kind of just almost complex. Then this S is just smooth. So the zero set of smooth map, it can be horrible. So what's good? What we need to mention is that somehow, if you just know X, this doesn't have enough structures. But if we include this BESC as a part of the structures, your X may have more kind of understandable things. You just have horrible spaces, then that you can never understand. But if you have this chart at each point, then you may do some things because it's easier.
Is there a transition in this?
Yeah. That's a key point. So we need to define coordinate change. But I think, if you start defining coordinate change, it's a kind of complicated thing. So what I want to explain is I don't explain coordinate change today, but I want to explain if you under certain situations, I mean, you can define this kind of chart in a moduli space, and how to do it. That's what I want to explain.
If you don't define overlap, an arbitrary compact subset of Euclidean space has these charts.
Sure. Yeah, sure. So to define coordinate change actually is a key issue. That I completely agree. But I just want to say today that there is a notion of coordinate change, which makes you to define fundamental class, but still. But then I just want to explain that there is cases that you can obtain this picture. So, but before that, I want to go back to the history a bit. So let me start with the Lima surface. So we consider this kind of object. This is I call marked Lima surface. So I want to explain why this kind of pictures, like expressing the moduli space as a zero set of certain maps, came up. It came from the study of deformation theory of complex structures. So I want to go back to that history. So we consider marked Riemann surface. This means that this is a two-dimensional, real two-dimensional, or maybe complex manifold. Maybe it's better to write one-dimensional complex manifold because there is no confusion. One dimensional should be. So we have a one-dimensional complex manifold which is compact without boundary. Then we consider Z. This is a point in sigma, and they are all different. So there is a so this is a very classical things. Then the theorem. I don't want to prove this theorem because this is too much famous. But it's a kind of theorem. It's just if this assumption is not so much necessary, but I just want to explain this. Put it to simplify. If the automorphism is trivial, there is a universal family of deformations. Because I want to use this theorem, so.
What's the second coordinate? Sigma.
That's something I want to define. This is automorphism, which I define now. This is a set V of, this is a biholomorphic map, and V preserves this marked point. So, for example, if sigma is just S2 and there is no marked point, then auto is a PSL2C. It's not finite group. And if sigma is a tori, then it's also very big. And this the trivial is a bit too strong assumptions, but I want to remove it later. But somehow, and this is known that I think I don't know. Maybe I think this is Riemann, right? At least as classical as that kind of things.
But when you say a universal family of deformations, what do you mean?
Yeah, that's something I want to explain now. Okay, so I want to explain this notion of universal family of deformations. So suppose you have this U, this is some open set on Rn. Maybe in this case it happened to be complex, but I want to, so you have this fiber bundle.
How many points are forming the Z?
This any, so L is fixed. So fixed number L. So you have a fiber bundle, and whose fiber is sigma. This is, and then we assume this S, and S is L sections, smooth sections. And then we have just this, and something else we have is for each alpha on the base space, you take this pi inverse alpha. That is sigma alpha, and we we have J of alpha. It's a complex structure of sigma alpha, and this depends smoothly on alpha. I think this notion can make sense, right? So this is a setting, and maybe one can say that Si alpha is different to Sj alpha. Yeah, by kind of disjoint sessions. So this is a notion. So
Smoothly varying set of holomorphic things.
Just everything is smooth. You have a family of
Varying set of holomorphic things.
Yeah. Smooth invariant set of this almost complex structure on sigma. So this guy I call this. So I think this formulation due to Kodaira-Spencer, but this guy is called C-infinity family of complex structures.
Sigma could be null, right?
Pardon? No, still smooth. No other thing I will go later, but not today. Because this is a fourth kind of several course. So I want to explain this simplest case. So this is a notion of this. So then the whole day is called a C-infinity family of complex structures. Maybe family of deformations.
Well, this is not definition of universal.
Yeah. But still, this is just a definition. I want to explain what I mean universal now. So the notion of universal is the following. Universal is the following. If we have this any sigma prime, Z prime, this is L point, which is epsilon closed. I will explain what this means soon. Two original things. So this notion to be explained, still explained, but just a while. It's something closed. Then yeah, maybe this diagram might be better to keep. So there exists unique alpha on this base space, and unique V from sigma prime to sigma alpha. So sigma alpha is a pi inverse alpha. This is a biholomorphic, and V Zi is zi prime is zi, no, not zi, si alpha. What else? That's all, right? So you have I'll explain this soon, but you have anything close to sigma z, you have a unique point on the base space, so that what you see on the fiber is bi-holomorphic to the given one.
Then you will say this is the universal.
Universal, yes.
No, but that does not define topology. To define topology, you have to take families of things to begin with.
Yeah, but I think I need to, so if I define this notion, then this is rigorous definition.
Well, you have to define topology on the base.
But this U is a manifold, open set.
Yes. So but to define it as being universal, there is a U topology.
So you don't agree? So first I will define this notion, right?
The definition is logically complete. I mean, definition.
It doesn't define topology?
No. He said, he just gave a definition. Relative to this undefined notion, he's given a definition.
Yeah.
But maybe Alexi's point is, take the discrete topology. Suppose U satisfies this. Now take the same U, but with the discrete topology and the induced topology on C, it'll still satisfy this.
It's the opposite of Rn.
Well, I thought the universal family was meant to be that if you had any other family, then it would somehow...
Yeah. Yes, I know that definition, but I wrote it in this way because it is suitable in the case when this is obstructed. But it is...
I think you have to...
Okay, we assume this is connected. Then probably this is enough. Corrected open set.
It's a little open set in Rn.
Yeah, if you take it open set in Rn and...
Connected.
Yeah.
Then this is equivalent to this well-known definitions.
Then you have to worry about that topology of a universal family.
No, we don't do it yet because we just this is a local problem, deformation theory. Yeah, connected probably is necessary. And this epsilon closeness is not so difficult. So we just say that this is epsilon close. Epsilon close is as there exists f sigma to sigma prime diffeomorphism. So that if you take this complex structure of J and you take this different structures, you take secant norm is smaller than epsilon, and you f of zi is your prime. So this is the epsilon closeness. You can fix k, and you can fix any Riemann. Maybe this is safer, right? I want to change the order because I want to fix something on sigma. This might be safer. So if you fix any Riemann geometrical C, then you can make sense of the secant topology. So if you just kind of by transforming the diffeomorphism, the complex structure is close to epsilon, and the marked point just corresponds. This is the definition of epsilon closeness. And you take these particular definitions, then we can prove these theorems. I don't know if it is, but this is at least very classical. And if you see this statement, we can prove that this universal family is in a reasonable sense unique if it exists because of the using this uniqueness.
So why do you want to do it this way rather than the more standard way of any family is induced from this?
In general, I mean, I want to go to the next case when something is obstructed. So in that case, universal family does not exist on this open set. So to say that this kind of unique exists and unique is a kind of harder to define. This way you can generalize directly. Okay, so I state these theorems, and this I think is very much classical, and I don't want to prove it. So now, this is something like, in this case, so I don't define this moduli space itself, but at least locally, this U is a moduli space of a complex structure of your Lima surface. And you can group them together to get global things, but still, I stick on working on locally. So this U, open set of Rm, actually this is R6G something, or kind of famous dimensions, is a open chart of your moduli space. And my purpose is to do something similar in the case you have maps. And I just want to skip something about the history. So I mean, this is the case of this complex dimension 1, and this is very much classical. And in 50s, codiron spacer generalized this to higher dimensional complex manifold. But then to generalize this story to higher dimension, so this kind of formulations using this smooth family, then define this kind of universality just started. But then,
that was too fast. What?
I mean, in 50s, codiron spacer generalized this kind of story. In the case, this sigma has higher complex dimensions. And in that, I mean, they use this kind of formulations using C-infinity fiber bundles and families. And then they want to generalize the theorem I stated, or rather more kind of categorical statement, which suggested by John and other people, and Alexei and those people. But then it comes in higher dimensions. If he just states this particular statement, it is not true. So in complex dimension 1, you can prove these theorems. It's classical. But if you try to prove the same theorem in higher dimensions, it is no longer true. So you don't have this open set in a Euclidean space as a kind of universal family. It means that if you deform your complex structures, the family of kind of the set of the deformation of your complex structure is not an open set of Euclidean space, but is in general singular space. So that's what these people found in the 50s. And then this comes to this Kuranishi. And what Kuranishi found is that this U, if you just take U as an open set of CM, then you cannot cook up this kind of families. But you allow this U to be a zero set of certain holomorphic map between complex spaces, then you can prove similar statement. This is what happened, what he found in something like the 1960s. Then I found that recently, around the same time, one of the Kodaira students, it's called Horikawa, tried to generalize this formalism to the case when you include maps. And he proved some things, but he don't join this to this Kuranishi's work. But that somehow kind of people knows. But then I want to restrict on the case of curves. Then you include the maps. Then even in the case of curves, you are in a situation that this U, this universal family, that is not an open set of Euclidean space, but is something singular. And that is related to this problem I just mentioned. So
you're saying the Riemann theory, beautiful. The extension of Kodaira spacer was obstructed. It was dealt with by Kuranishi in a certain way. The J-homomorphic curves, moduli space is obstructed, and you're going to deal with it in a similar way.
Yeah. But that fact is not so much a secret. I mean, Donaldson and those people already used it in gauge theory. So that kind of ideas are kind of around in 80s and 90s. So, what I want to say. Yeah. So now, let's take xj. So here, everything is still local theory, so I don't need simplex structure. So j is almost complex. So x is two-dimensional manifold, and j is a map here, so that j square is minus 1. So this is almost complex structure. So now I want to study these situations. Then you have sigma, it's a Lima surface. Then you consider u from sigma to x, and we call it some j-holomorphic or pseudo-holomorphic. It's somehow here's this du with this j minus du, and this j of sigma is 0. So this is just a differential of u is complex linear. So we consider this j-holomorphic maps. So maybe I can just state one theorem. So we consider this sigma z u, right? So this is a marked Riemann surface, and u is a holomorphic map, j holomorphic. So what I mean by this obstructed families. So with this, we consider these situations. Then we have so now you know the things a bit more become very the thing you have get bigger. You have these things. S R M F X. What else we have? Yeah, you have this S. So, maybe I need to assume this one I will kind of relax a bit later, but somehow I just want to assume that this is trivial. So this means that you have a V from sigma to sigma, which is biholomorphic, and B of Zi is Zi, and U composed B is U. So, I mean, if you just remove this is a group of automorphism as before, but you include U, so you have this extra conditions. And for a moment, I assume this assumptions. There's no automorphisms. Then the claim is that there exists this diagram, which is universal. I think this universal is not a good word because I don't like to call it universal. Universal probably might be better. So this is the claim. So I need to explain what it means, but somehow, if you just forget this part, the picture is very much the same of the deformation theory of complex structures. But you have some extra things, X and this one.
So what's the claim again? What's the RM?
That's something I'm going to explain. So what
is the claim?
I mean, the claim is such a diagram exists.
So there is some RM, and the V is the U of Davis theorem?
V is some open set. That's bigger than U. But V is open set of Euclidean space. And you have a C and X. And you have this. And this has some property, which I will explain now.
So which parts are given, which parts are...
I mean, given is sigma UX. So given sigma x u with this property.
And that is presumably one point of V, or rather.
Yeah, it's actually one point of view. Yeah.
It's one fiber.
Yeah.
Restricts.
Yeah.
It's an extension of it.
Yeah. But I didn't explain what it is, so I want to explain what it is.
Okay.
Yeah. So
given sigma u, then there is what? Can you?
There is this diagrams, but it's universal in a sense I'll explain below. And this diagram I still did not explain.
So if I remove X and RM, it's exactly what I had before?
No.
Smooth family?
Yeah, this is, so first thing I explain is that this is a C-infinity family of deformations of complex structure. You first of all, you have a C-infinity family of deformation. This is not necessarily a universal family, but you have some C-infinity family of deformation of complex structure. And this S is a map. This is the C-infinity map. U. Then F is again C-infinity map on this total space of the fiber space. But then if alpha is in V, so that S of alpha is 0, then we restrict S to this pi inverse of alpha. So pi inverse alpha is this fiber is a Riemann surface. This is J holomorphic. I think this is the definition of this family. So you have some smooth family. So any B, you take a fiber, you have a complex Riemann surface plus marked points, which is given by these sections. And if you restrict F to this Riemann surface, you get some smooth maps. But you don't claim that this smooth map is holomorphic always. Only if this S is 0, then it is holomorphic.
Oh, so your S now is a different S. Your S before.
This S is section. This S is the Kuranishi map.
This is.
Yeah, so that's why I use this character and this character. But you do not like it. Maybe rated K.
Very complicated.
Okay, let me rate it K. K is because K is this is called Kuranishi map actually. So, but later on,
Before S was the point. S was it gave you your mark points.
I mean, I have also this. So you have two. These are different notions. You have this S, which gives a.
So now K. So when you say S alpha is 0, you don't mean that S which gives.
K. This is K. This is K. K. Yeah.
I see. So
Yeah.
So your RM now is
It's obstruction spaces.
Obstruction space.
Yes.
Because before you were saying that V was sitting inside RM.
Yeah, so maybe I'll use N and M. So before we have this picture, you have a smooth family of almost complex structures, and we claim that there is a universal family among them. So if you include the maps here, then we need to include this kappa, which I call a Kuranishi map, so that you have this family, and this one is J-holomorphic only in case this map is 0. If this is not 0, it may not be holomorphic. And I still need to explain what I mean by universal. At least kind of, I don't know what I mean. I don't want to call it universal because in this formulation this is not unique. So earlier formulation of this deformation of complex structures, such a picture exists. It is unique. But even if I claim some kind of universality, but it doesn't guarantee that this is unique. And this point is actually important because this is related to the fact that this Kuranishi structure is not canonical.
But the trivial point is you need the word epsilon close, so and that's going to be the obvious definition.
Yeah. Yes.
You didn't say it now, but epsilon close is included in this.
Yeah. That's something I
That'll
noticed.
be the combination of the obvious closeness on maps F.
Yeah. That's something I wrote down. So this universality in this UX sense means the following thing. You have any sigma prime, Z prime, U prime, which is epsilon close, which I will soon explain, two original ones. Then there exists unique alpha with kappa alpha is 0. And there exists unique B from sigma prime to sigma, so that this is a sigma alpha, this is biholomorphic. So that if you compose V with this F, it is equal to U prime. So that is a universality. I mean, the moduli space of this sigma alpha plus this J-holomorphic map locally correspond 1-to-1 to the 0 set of this Kuranishi map. Because only that one is a kind of, this map is a holomorphic only on a 0 set of kappa. And the claim is that if this is close to the given one, then it corresponds uniquely to this pair. So this gives some kind of a...
Wait, I thought you said something failed in the analogy with the previous case.
I mean, this means that, in a previous case, if such a family with this property exists, then it should be unique.
With this family, this solution is not unique.
Yeah, this solution is not unique because if you just increase V, if you put the extra factor, and if you put the extra factor here, and S is just kappa is identity of that factor, then 0 set of kappa does not change at all. So you can increase things, but then it's still this property. But so the uniqueness definitely fails.
No, because this gives a presentation of the analytic.
Yeah.
What is the role of Rn? I mean, what would happen if you just take Rn and say set K to be 0?
No, this is opposite. And the 0 set of K can be extremely singular.
But that's part of Kuranishi.
So only the 0 set of kappa you have a holomorphic map.
I think he's saying
that this is universal in the sense that if you have any family like this and you restrict it to 0 set of S, I can map that to the universal.
That's correct. That's correct. But this, for example, this V and kappa is not a kind of a well-defined meaning.
But I mean, in Kurnishi's picture, you have this. You take the first some number of eigenvalues, eigenspaces of your map, and you can increase the bigger eigenspace. But they're the same.
Yeah, but in the case of this Kuranishi picture, for example, if you assume this is a complex space, and if kappa is a holomorphic map, you can just take this 0 set of this kappa, and you put sheaf, some sheaves which you can give these structures, and in that sense you get a very good, well-defined spaces. And if you try to do it in this infinity world, you have to take this germ of smooth functions and divide it by this kappa. That's not so good. So Joyce tried to do that kind of thing, but that's harder. So,
I mean, what I understood of Joyce was, I mean, he was somehow assuming that there was some universal picture like that, and he thought it was up to the analyst, you know, the symplectologist to prove it.
no, I mean, you know, his point is, you know, the point is that somehow, you know, so the point that this non-uniqueness, the reason is non-uniqueness is we know we can control something what happens in the zero set of kappa, because it is the honest modular spaces. But you go away from the zero set of kappa, so this guy can be quite arbitrary. So you have no obvious control. But you know, the idea is somehow Kuranishi structure is just to kind of enrich this modular space quite a bit to get this B. On the other hand, if you just stick these pictures, then you have a smooth things. I mean, B. For example, if you want to define differential forms, you can use this differential forms on B. That's something good. But on the other hand, because you cannot control anything outside the zero set of kappa, then this picture you cannot expect to be unique or canonical. So you want to get something canonical, then an idea is to find some structure which lies on the zero set of the kappa, so that it gives enough information what happens in this small neighborhood. And that's what this Joyce is trying to do. And in a world of complex analytic geometry, if you remember the sheaf of holomorphic functions on a germ divided by this generator kappa, then you know have enough information. That is what this discovery of several complex variables. But one cannot expect that kind of things happen in infinity world. Holomorphic function is very good things, but you just consider ring of smooth functions.
Is there any chance of working in the context of Whitney stratified spaces? You get some sort of different.
It is a possibility, but you know, this kappa can be quite arbitrary, and this B cannot be, in general, cannot be quickly stratified.
I'm gonna turn to the analyst and say it's not really an arbitrary kappa you're talking about. You're talking about something that comes from a nonlinear.
Yeah, but you know, for example, you want to include this Hamiltonian things. Then Hamiltonian perturbation, you can include any smooth functions. So I don't expect that V has any good properties. It can be Cantor set, for example. Horrible set. And that's important case of this simplex geometry, so it's inevitable. Okay, I don't know. So
the topological space, the germ of the topological space is zero set of.
Yeah. As a topological space, the modular space is well defined. It's vectorizable space, and it's compact. It's okay, but topological space, it's not quite enough.
No, but it's also embedded in the space where the equation is defined.
Yeah. So this picture somehow means that you can embed these things to some finite dimensional things locally. And the point is that the point of this thing somehow you can do this locally, and then if you go to this kind of global things, you need to glue this kind of pictures. But you know, to glue this non-uniqueness causes some problems. I mean, you have some canonical structures, then gluing is a kind of immediate things, if one knows the correct word. But since this V is not canonical, you can define this V by some particular ways, but it's not canonical. So it means that you need to be careful to have a global picture. But the idea is that you cook up this picture locally by some particular ways, and you try to use these ways to show that you can glue this picture globally to get kind of finite dimensional reductions of your modular space in a consistent way at every point, in the neighborhood of every point. And that's what this Kuranishi structure is doing. Okay. Yeah. So I don't know how much I can say about the proof of this, but I want to explain some main ideas of the proof of this. So I mean. Yeah. Okay. I mean, you know, there is the fact that this is a Kuranishi picture is written somewhere, and one can write it in this particular way from that, but not in this particular way it is written.
This is standard.
Yes, this is standard. Yes.
If you're not taking oil surfaces.
It is standard. Yes. For example,
Abstraction bundle, we take it singular.
This is just a.
In my paper, we wrote down a proof of this in the case of spheres, for example.
I mean, you know,
We didn't do hygiene surface.
I mean, in the case of this sigma is smooth, then I think if you ask Gromov, he knows 20 years ago, but it's Gromov. And if you ask somebody else, then, I mean, you ask, for example, you ask Horikawa whether he can prove this, I think he can prove it 30 years ago. So this is not a new thing, it's standard. And Horikawa do this kind of thing in case this is integrable. So if this is a kind of usual complex manifold, you have better situations, but he used analysis, so you can just transfer that kind of proofs. But not obstructions. But if you ask Kuranishi 30 years ago, he can prove it, I think.
So you're not using symplectic here.
Yeah, but yeah, I mean that's almost complex because this is local picture. Simplex structure just come in compactifications. So if you study modular space of J-holomorphic locally.
No, I'm saying in this theorem, you don't need
No.
roll.
Yeah, it's just a J.
Just a J. Yeah.
It is because it is local theory. Local theory of pseudo-holomorphic curve, you don't need anything about simplex structure. If you go global, you need it. So I just want to say some of the ideas we need to it. Then, yeah, maybe I think also I want to include the case that there is a finite group. If this is a finite group, so finite group. Then in this case, you can.
Did you define epsilon close here?
Sorry. Okay, let me explain. So I want to explain this epsilon closeness. This is epsilon close, sigma zu. This means that you have another f, diffeomorphism. So that you f of this j sigma, better to start it the other way because I want to fix something only on sigma. F star j sigma prime minus j sigma, ck is smaller than epsilon, f zi prime is zi, and u f, I'm sorry, this minus is not correct notation, but you can see what it means. The difference is smaller. This is epsilon closeness.
And you don't care what the differentiability is here?
I think if you fix k enough large, you take anything, it's basically the same thing. It's holomorphic map, so.
Okay.
Elliptic regularity. And so in the case of this automorphism, it's non-trivial.
What is the least thing you can take for this norm so that this theorem is still programming? Can you go L1P or, I mean, what's the minimum?
L1P, probably, yes. I mean, basically minimum thing you need is just, there are some exponent. You can just, it's small, then you can use elliptic regularity to go arbitrarily higher. Probably L1P. But, yeah. Yeah, and I mean, maybe I just explain the proof and maybe something else later on. So there is two cases. The first case, the easy case, is this case. So let me remind you. We take the first case. We take assumptions. This triple is an identity. So this is a strong assumption than this. This means that if you just take the source of Riemann surface, then it is isotropic group is finite. So let me show you some example. Oops. Then you take some examples. For example, if this is an empty set, the sigma is S2 and x is S2, and u, z is, for example, z. Then you can easily see that this guy, this is PSL2C. You have a biholomorphic map of S2, it's PSL2C, it's huge group, so you cannot use, so this doesn't satisfy the strong assumptions. But if you take this guy, then this is just unit. So we have to include this kind of cases. But the simplest case is this case. Because why this is simple? Because in this case, we can use previous theorems. So what we can use in this case, so you start with this universal family of deformations. Let me write the C note to distinguish it. So you don't have this, you have this universal family of complex structures. In this additional assumptions, you have a universal family of deformations. So you have of deformations of complex structure of sigma z. So this is a classical theorems. Riemann, yeah. And then this is a fiber bundles. So we shrink V a bit, then we may assume that this is a, so in the infinity sense, this is trivial. So this bundle is trivial. I mean, C naught is sigma cross V and V, and this Si of alpha is just this Zi alpha. This Zi is independent of I. So you can just trivialize the whole picture together with sections. This is smooth fiber bundles. So everything is locally trivial. What good it is, so somehow, just mentioned before, somehow, if you do this, then the problem about the diffeomorphism group is just gone. Because you have this family, and your equation is something like this, right? Your equation is, you have this U prime from sigma alpha to x, and your equation is J U prime minus U prime, J alpha is 0. I'm sorry. J du prime, maybe let me write this way. Let me take du prime, and we divide it to this d u prime plus d bar u prime. I want to put it alpha. So this is a complex linear part. This is the anti-complex linear. So it means that the d bar alpha u prime lies in this home. No. It's a sections, smooth sections of sigma prime of this tangent bundle tensor 0, 1 alpha. What it means? This space is a home from tangent bundle of sigma to tangent bundle of x. So you have z u prime z, but it's a anti-complex linear part. So you just differentiate d of u prime.
Not necessarily.
Yeah, you get a real linear map. Then you divide it by to this complex linear part and the anti-complex linear part. Then this is by definition is anti-complex linear part of this differentials. So you got this. And of course, this splitting depends on alpha. You use this alpha. Alpha is this complex structure on the Lima surface. So your splitting depends on alpha. But then your equation is this equation. So this is your equations. And what's good here is this is a nonlinear elliptic PDE. This is elliptic. That's good. This is a smooth family of nonlinear elliptic PDE. It depends on alpha, but everything depends on smoothly on alpha. So we can use this to do kind of Fredholm theory or something like that, modular theory. And there is a similar story in Yamil's case. In Yamil's case, people do the following things. Suppose you have this kind of, I'm sorry, this is something called ASD, anti-self-dual equations. And what's bad is that this equation is not elliptic. Yamil's equation is not elliptic because you have a symmetry that's called a gauge symmetry. So this is not elliptic. So what people use is just not using this, but also they use this d a0 star a minus a0 is 0. This is called a Coulomb gauge. So they fix some. So the plane of rho, the second equation is to kill this infinite dimensional symmetry of gauge theory. So if you combine this and this, then you get honest elliptic equations. That's the way this Yamil's theory works. But what's different is a kind of, so gauge theory is something like a gauge transformations. So you have a gauge group, gauge transformation group. And this is infinite dimensional group, and this somehow is similar role of the diffeomorphism group of sigma. You have an infinite dimensional symmetry in both theories, and a gauge theory it's a group of gauge transformations. In a pseudo-holomorphic curve, it's a group of diffeomorphism. if you just allow to change this complex structure of the source and this U together, and then you need this big symmetry. And this big symmetry is not so good. Probably this is even worse than gauge transformation group, because diffeomorphism is always harder to study than gauge transformation. So we want to kill this diffeomorphisms. That's one point. Then to kill these transformations, so we can split. In the case of holomorphic curve, we can split this problem into two parts. One is just you consider this moduli space of complex structures, and then at the point you fix this, you get this universal family of deformations of complex structures. Then this is killed already. That's why this equation is elliptic. You don't have any more symmetry remains. So you don't need to study this group if you consider this way. That's something I'm explaining. Okay, so now this is the problem. And yeah. So I want to study these problems. So now the rest is actually a kind of standard, but let me do it for something like this. So you have this U. So I want to consider linearized equations. So it's the following thing. So you have this U prime. Then you take V, it's a sections of pullback bundle. Then we consider this linearizations. It's the following. We take this exponential. This is bad notation, but I want to use this notations. This Z is an exponential map of this U prime Z of epsilon VZ, right? I mean, this is a vector field, so you just take this point and you just explain. So you have a map here. Then I want to take this differentials and d bar alpha U prime plus epsilon B and take epsilon equal to 0. So you have some things. And this is the operator. So this is, of course, the linearized equations. This goes from to C infinity of sigma U prime star dx to C infinity of sigma of U prime star dx tensor 0, 1 alpha. So this is then this one I want to write d U prime of d bar alpha. So you have this linear operator. It just take differentials of these equations to the tangent directions. And this, for the elliptic theory, says that this is a Fredholm operator. So this operator is Fredholm. So this is a very much standard fact. You have this elliptic equations, and its linearization is elliptic equations. So this is mainly a elliptic theory. So we consider the case U prime is U and alpha is origin, maybe alpha 0. Then we take finitely many Wi. Then we relax. So we then kind of. So this is the sections. Of this. Then the restriction is just you take the image of this operator. Then you take the sum over all this Wi. Then this is everything. This is something we assume. You can do this. This is Fredholm. Fredholm means that cokernel is finite dimensional. So you can just choose finitely many sections so that it together with this it gives everything. Maybe direct product may not be good. Probably. Then somehow I don't explain it today, but I think in this situation it is still not so much precisely. You can just take arbitrary. So why you can somehow take some choices. So this is so that such that this is the infinity of this sigma u prime star dx and this 0 1 alpha, so that this guy at this origin just coincides with this. So you have just sections at one point, so you can just extend it to the smooth family, and it is you may assume that it is enough smooth. And I mean, if you go on, I mean, in a more delicate case, like the case when this sigma has a singularity, you need to specify this kind of choice a bit more precisely. But at this stage, you can quite arbitrarily choose it so that it depends smoothly on u and alpha. Then the point is that we replace the equation to the following equation. So the original equation is something like this. This is the original equations. But then we replace these equations so that d bar alpha u plus ci wi u prime alpha is 0. So then the cu prime is a kind of an alpha. So unknown is u prime alpha and ci. This is a real number. So originally you require this to be exactly 0, but you allow a bit finitely dimensional extra terms. And what good is just this one? We can apply implicit function theorem. Implicit function theorem to these equations. Because maybe I just want to do, I mean, you just linearize this at the origin, u0 and alpha 0. This term, linearization of this term, so I mean linearization of this term gives this du d bar alpha 0. And then if you take this the differential with just the ci directions, it gives this wi. So linearization of this equation is surjective at the very origins. So it's open conditions. You shrink this domain a bit, then you can apply implicit function theorem. So what do we mean that if you take the solution set of this guy, this is certainly finite dimensional manifold. So the set of solutions u prime alpha ci will satisfy this is smooth.
If you look at Milner's old notes where he proves C1 transversality theorem, this is the same proof.
Really?
Add perturbations.
Yeah.
Makes sense.
Yeah.
Right.
But I think this is basically Kuranishi's ideas.
Yeah.
And so this is actually our space B. So you have a bit bigger things, which is smooth manifold. Then we have this map from B to R of, so this is 1 to n, as kappa, right? Kappa is just we have this element here, and we associate to this C1, Cn. So this is kappa. So what is that object? So I think I finish this particular case soon. So we have this map B to this U0. So this is just to forget Ci. U dash, no, I'm sorry. This is just a alpha, right? Alpha U prime Ci. So we just associate to alpha, and you have this universal family. So you can just pull back. Just pull back. This is smooth map. So you have this C infinity family of complex structures on this 4 things. This is C0. Then the map is just, of course, we can just define. So F from C to X is following. So you have element C. Then so suppose that you have a So suppose you have an element here. So it's something like a Z element of C. You may see it's this guy plus 5 up here, right? So this is Z alpha U Ci, and this Z is supposed to contain sigma alpha, right? Because if you have an alpha here, the fiber is if you have alpha here, the fiber is sigma alpha. So you take a fiber product. So you have an element here, then the element fiber is sigma alpha. So the element here is a pair of this guy plus a point on this Riemann surface. Then I want to send this map, of course, to U prime Z. So this is this map F.
So
X is the almost complex manifold, finite space.
the ambient manifold.
Yes.
Oh, I see. Because I think before, wasn't it? Your moduli space is at M.
Yeah.
Okay.
So this is a map. This kind of universal map. And if you restrict, so this is a construction that you restrict to this fibers. Then if this S, so this is the final point. If S of alpha is 0, then U prime restricted to this fiber, U prime. So then U prime is a J holomorphic with respect to small j alpha, right?
Kappa. In this context, you called it kappa, right?
Kappa. Yeah, kappa. Yeah. I'm sorry, I always misunderstood. Yeah. If kappa alpha is 0, then by assumption, it's what we know is just the d bar of U alpha plus sigma Ci Wi is 0, but this guy is actually 0 because Ci is kappa. So if this is 0, then this is an honest holomorphic map. So you get this map. So this one, if you restrict the fibers on the 0 set of the kappa, you get a holomorphic map. Out of the 0 set, you're not holomorphic map. So this is Ci. This is Ci.
In terms of the CIs?
Just exactly cap Ci.
Collection of all CIs.
So I mean, yeah. So this is the construction. So you can just enlarge the equation quite a bit, including this terms, and then this kappa itself is just this coefficient. You enlarge. So in this way, you can get an always smooth manifold with this kappa, so that in this 0 set you get this holomorphic map. But it's outside the 0 set, it's slightly different from holomorphic map. So this is a way, but as you see that there are many choices. The biggest choice is I think this Wi, and how to extend it to the neighborhood. It's a kind of arbitrary choice, and I don't know any kind of very canonical way to make it. Okay, so now this is the time.
But if you keep in mind, the people working on this are geometers, and they think about wanting to get a moduli space, maybe a stratified space, maybe a cycle, get something nice, right? If you think about your objective, you just want this homology information at the end. These sort of perturbations are
right.
Lovely. They're embraced by the ideas. Whole idea of homology is you take random approximations to things, they're all homologous and so on. These ideas should be put in very forcefully, remembering the ending goal. And a lot of these technicalities some of them might just disappear. So I'm imagining.
My feeling is that there is an analysis on the topology and geometry concerns, and if there is an analysis part, and if you try to do this analysis part using just by algebras, probably it's not so easy. You need to put some analysis, and this way you reduce this infinite dimension thing to finite dimensions, and once you reduce it to finite dimensions, then there are a lot of room. You can use this topological ideas. There are many particular ways to make geometrically transversal, or to use kind of some algebraic argument, as you said, kind of just chain level argument to make it. But if you start from infinite dimensions, then probably you just try to do this using some homological algebra kind of things, general topology type things. Probably you are not, you may mistake sometimes, because it's a kind of actually difficulties. So this idea is kind of, you reduce everything to finite dimensions.
No, but the topology ideas have to come in before you reduce to finite dimensions, because you have this Fredholm equation that's guiding the thing. And these choices are made relative to that. The information has to be remembered too when you're an algebraic topologist. Remember that, and then you get into finite dimensions, and then you're happy and you do that. So you have to remember the equation.
Sure. Yeah. I mean, this kappa is something which remains in Fleming equations.
Yeah.
Well, then maybe you could imagine there's more structure than your abstract definition of recursion.
Yeah, probably, yeah. But somehow,
Trying to do this purely combinatorially in some way, you could imagine some geometric differential topological structure that these Fredholm operators give you, nonlinear Fredholm operators give you.
I was going to suggest that you should film these courses by Kenji and
We are filming. Oh. Suggestion accepted.
So I'll stop here. Thank you.